If we take our equation from before, that the total entropy change is equal to the entropy changes for the system and surroundings added together, and we substitute negative delta H over T for the delta S surroundings, we can rearrange things and define a quantity known as the Gibbs free energy change for the reaction, delta G. This delta G is equal to the enthalpy change for the reaction minus the Kelvin temperature times the entropy change for the reaction. So everything is defined in terms of the reaction, not the surroundings. This delta G is what directly determines whether something is spontaneous or not. Since it's proportional to negative delta S total, and delta S total must be positive for a spontaneous reaction, we get the results here. A negative value for delta G indicates a spontaneous reaction, a positive value indicates a non-spontaneous reaction, and a value of 0 indicates a reaction mixture that's already at equilibrium. Due to the fact that the Kelvin temperature component of this equation is always positive, since attaining temperatures at or below absolute zero is physically impossible, we can say certain things about the spontaneity of a reaction based on the signs of delta H and delta S. For any exothermic reaction, where delta H is negative, with a positive change in entropy, where delta S is positive, the quantity delta H minus T times delta S must always be negative, so any such reaction will always be spontaneous, regardless of the temperature. For the opposite case, an endothermic reaction, with a negative change in entropy, so where delta H is positive and delta S is negative, delta G will always be positive, hence any such reaction will be non-spontaneous at any temperature. Things become a bit more interesting when delta H and delta S have the same sign, either both positive or both negative. If both delta H and delta S are negative, the reaction in question will be spontaneous only below a certain temperature, where delta H outweighs T times delta S. Above this cutoff temperature, the reaction becomes non-spontaneous. Conversely, when both delta H and delta S are positive, the reaction will be spontaneous only above a given temperature, where T times delta S outweighs delta H. Below this temperature, the reaction will be non-spontaneous. This will have come up in Chem 1211, but as a reminder, the thermodynamic standard state of a substance is the most stable form of that substance under 1 atmosphere of pressure at 25 degrees Celsius, and with all substances in solution having a concentration of 1 molar or 1 mole per liter. These are the conditions under which all the values for enthalpy of formation and standard molar entropy are defined in the appendices in your book. We can indicate that a thermodynamic quantity applies to the standard thermodynamic state by using the degree symbol next to it, as shown in this equation for calculating the standard Gibbs free energy of formation for a reaction. For example, let's use provided values for delta H standard and delta S standard to calculate the standard free energy change for the synthesis of ammonia, NH3, from nitrogen and hydrogen gases. This is an exothermic reaction with delta H equal to negative 92.2 kilojoules. The delta S standard is also negative, at a value of negative 198.7 joules per Kelvin. Plugging these into the equation for delta G standard and converting 25 degrees Celsius to 298 Kelvin, as well as accounting for the fact that delta S uses units of joules per Kelvin, while delta H is in kilojoules, we arrive at an answer of negative 33.0 kilojoules. Since this value of delta G standard is negative, it indicates that the reaction as written is spontaneous at standard thermodynamic conditions in the forward direction. Because both enthalpy and entropy are state functions, delta G is a state function as well. That means that if we know the standard Gibbs free energy of formation of all the reactants and products in a reaction, we can simply add up delta G of formation for the products and subtract delta G of formation for the reactants to get the standard Gibbs energy change for the reaction without having to calculate it from enthalpy and entropy. Standard free energy values of formation are known for many common substances and are listed in the appendix of your book as well. As with enthalpies of formation, free energy of formation is defined with respect to the standard state of each element making up the compound. So any pure element in its standard state definitionally has a delta G of formation of 0 kilojoules per mole. There are many values for common substances listed in your book, so don't memorize any values here. They'd typically be provided for you as needed. And of course, if you are provided with these values, you can calculate the free energy change for a reaction based on the reactants and products. Feel free to pause the video to follow this example in detail, but it's largely redundant if you can follow the products minus reactants example for calculating the entropy change for a reaction from a few slides ago. Otherwise, let's move on to what this has to do with equilibrium. We've discussed how to calculate the standard free energy change for a reaction via a couple of different ways, but of course we can also consider systems under non-standard conditions. For some combinations of reactants and products other than the amounts defined by standard conditions, the free energy change for a reaction, delta G, will be equal to delta G standard plus R times T times the natural log of Q, where R is the molar gas constant, T is the temperature in Kelvin, and Q is the reaction quotient. Remember, as shown at the bottom of the screen here, that the reaction quotient is the same as the expression for the equilibrium constant, but with initial concentrations or pressures plugged into the equation instead of the values at equilibrium. Let's consider the following example. Calculate delta G for the formation of ethylene gas from carbon and hydrogen at 25 degrees Celsius when the partial pressures are 100 atmospheres of hydrogen and 0.10 atmospheres of ethylene C2H4. Under standard conditions, this reaction has a free energy change of positive 68.1 kilojoules. To complete our equation, we need an expression for the reaction quotient, which, based on the reaction and its coefficients, is the partial pressure of ethylene divided by the partial pressure of hydrogen squared. Carbon is excluded from the expression since it's a pure solid. If we plug in 0.10 over 100 squared and take the natural log, we get negative 11.51. We then plug this in for the rest of the equation using 8.314 joules per mole Kelvin for R, 298 Kelvin for the temperature T, and a conversion factor since R uses units of joules, but delta G uses units of kilojoules. Taking everything into account, we get a delta G value of 39.6 kilojoules per mole, positive. Since this is positive, of course, the reaction is not spontaneous in the forward direction. Let's consider what happens to a reaction mixture as we approach equilibrium in thermodynamic terms. When the reaction mixture is mostly reactants, the reaction quotient will be less than 1, and so the natural log of the reaction quotient will be negative, and the free energy decreases as the reaction proceeds forward. Conversely, when the mixture is mostly products and the reaction quotient is large, above 1, its natural log will be positive, and the total free energy decreases as the reaction proceeds in the reverse direction. If we plot reaction progress, in other words, the relative ratio of products to reactants, on the x-axis of a graph versus the total free energy on the y-axis, we see a graph that looks like this. At some point between exclusively products and exclusively reactants, there's a point of minimum free energy, and this corresponds to an equilibrium mixture of reactants and products. It will, of course, be spontaneous for a system of pure products to proceed towards this equilibrium in the direction of the reverse reaction, since delta G decreases as it does. Likewise, a system of pure reactants can decrease its free energy by proceeding towards the equilibrium point in the direction of the forward reaction. And for an equilibrium mixture to proceed in either direction would involve increasing the free energy, and so would be non-spontaneous. Recall that when the reaction quotient is equal to the value of K itself, the reaction mixture is already at equilibrium. Also at equilibrium, delta G is 0 since neither the forward nor reverse reactions are spontaneous. Making these substitutions into the equation, we get the relationship between K and delta G standard. The standard free energy change, delta G standard, is equal to negative R times T times the natural log of K. Taking this equation into account, we can see that if we have a K value larger than 1, delta G standard is negative, meaning that a product-favored reaction is spontaneous in the forward direction under standard conditions, which is what you'd expect. The reverse, that a K value less than 1 gives rise to a positive delta G standard value, is also true. Let's consider this example. What's the value of Kp for the reaction shown here at 25 degrees Celsius? We can find the value of delta G standard by subtracting the free energy of formation of the reactants from the same for the products, and we get delta G standard is equal to positive 131.4 kilojoules per mole. We can then plug this into the equation to solve for K. Rearranging the equation, we get natural log of K equals negative 53.04. Exponentiating to solve for K, we get a Kp value of 9.2 times 10 to the minus 24th power, which makes sense as an extremely reactant-favored value for this reaction with an extremely positive delta G standard value. Anyway, that brings us to the end of this chapter. Thanks for your attention, and please continue to stay safe out there.